Morning everyone. So what I want to do today here is I want to give you a quick crash course of organic chemistry. In grade 12 we're actually going to do this as a full chapter. We're going to look at some of this naming that I introduced in this lesson and actually get up to the reaction stuff that actually is second year university stuff. The reason why I'm doing it for you in this bonding chapter, although in chapter 4 I'm not going to specifically be asking you name this compound, what functional groups, we're going to see this all in this lesson here. The hope of introducing it here is actually to help you in case you're predicting hybridization, in case they give you an organic molecule. If you know some of these basics organic, it might actually help you to draw structures a little bit quicker, and in that case it'll save you time on the test. The other reason I'm going to do it here is in regular chemistry 11 they also do this naming. So let's say you go back into regular Chem 12 next year. I want to make sure you're sort of on par with your classmates in that sense. Strangely enough, they actually don't do organic in grade 12 or first year, so you just touch on it a little bit in grade 11. Unless you really go into chemistry second year, third year, so you won't necessarily need this stuff. So hopefully just a quick overview of organic here. I'm going to give you a summary sheet later on which you can refer to, which will go over some of the main topics that we talk about, and let's just scribble over this one here. So for organic chemistry here, it does loosely have to do with sort of organic vegetables, things like that. Organic has to do with things of life. In this case here, we just say organic chemistry is the chemistry of carbon. Basically, a lot of the living molecules, proteins, sugars, amino acids, a lot of different building blocks of living things are actually based off of carbon. My student teacher used to like saying organic chemistry is like chons, so some other molecules or elements that are in organic compounds, well, CHONS. Typically, I would say C and H are the primary components. You might throw in some oxygens as you get to some sugars. As we get to larger molecules like maybe caffeine, DNA would have some sulfur in it. It would actually have some other of these as well. So why is it so special about chemistry of carbon? If you know from chapter 4 here, carbon actually is group 14. Carbon actually is 4 valence electrons, so it's sort of maximally equipped to actually make the most attachments. Remember, it's usually the unpaired electrons that do the bonding. Carbon currently has 4. When we take a look at methane, let's say I attach the rest of these with just 4 H's here, that already has 4 different attachments. We already need a hybridization, we already predicted shape and a whole bunch of that. So carbon is already at the best situation. It's tiny and it has these 4 unpaired electrons. Carbon has a property, I believe it's called catenation, where carbon can actually bond to itself. Every carbon, we're going to use this hint here, every carbon can make the equivalent of 4 bonds. So I should be able to see where those 4 unpaired electrons end up. This one here, so far I've just drawn a diatomic compound, right? Nonmetals are used to doing this, but carbon can actually do this again and again and again and again. We can actually make a long chain of carbon. That chain there will, in this lesson, be called a parent chain. We can end up forming rings, so I can have a square ring of carbon here, I can have double bonds of carbon, I can have many different formulations, I can throw on the other elements, oxygen, nitrogen. We can get really complicated really, really quickly. So a lot of the living molecules here are based off of carbon, and organic chemistry revolves around the chemistry of carbon. Because there's going to be so many different families and this is going to get so complicated so quickly, we need a way of categorizing them. Again, similar to what we do in biology, we see all the variation in life. We want to create a systematic scheme to try to put them in order. So we're going to start off here with our simplest family. We're going to do a lot of the basics and the naming rules here with this basic family, and then we're just going to extend it later on to other families. So the first family I'm going to do with you here are called alkanes. The main ending here is the ane as a suffix. Suffix comes after the word here. Alkanes are carbon-built compounds that only have single bonds. In fact, they're just going to be C single bond C. Now we know carbon itself has to have the equivalent of 4 valence electrons. It's not like carbon can actually have these unpaired electrons non-bonded. That would make carbon a radical, it would make it very unstable. Even though we're going to see with the naming of it, it comes directly from the structure itself. We assume that the remaining, sort of the other bits of it, are just going to be hydrogens. So in that case there, I'm just going to flush out the rest of them with hydrogens. Let's start off with the simplest alkane. Let's just do it on the side here. There's a couple of different ways of representing these. Let me just recap here. So alkanes, we're looking at single bonds. This is our easiest of families so far. And we're going to make it even easier here. We're going to mainly focus on hydrocarbons first. We actually saw this term here back in chapter number 1. Hydrocarbons only contain 2 different types of elements. Hydrocarbons are part hydrogen and part carbon. So these ones here only contain hydrogen and carbon. So if it's not the carbons I show you, you can assume that the rest of it is going to be carbon. So let's start off with the simplest alkane. Let's just start off with one single carbon. There's actually going to be many different ways I can represent this. So let's start off with, set up a sort of table structure here. We'll call this one here a structural formula. The structural formula will give you all the detail. So I have carbon. I know carbon has the equivalent of 4 bonds here. Let's let hydrogen saturate. Let's let hydrogen fill up all the other bits of it. Hydrogen only wants 2 electrons, an incomplete octet. There we go. That's our structural formula. That's methane. Leave a little bit of space here. I'm going to add what's called a condensed structure in a second here. So condensed structure or condensed formula. Remember, formula just means a symbolic representation. We're sort of going from structural, we're getting less and less detail. We get to something called a molecular formula. The molecular formula we saw when we did empirical formula, this was the actual number of atoms in each compound. And then we have our, what I'm going to call the You Pac name. Basically, there's a group, international, this is International Union of Pure and Applied Chemists. These are the people that set all the rules. So all the chemistry we've been learning has been this IUPAC. So usually when they say name these compounds, they're going to say use the IUPAC way of naming in the way that we're going to go over today. So in this case here, we have the structural formula. Great. I have C with 4 H's. So I know right away the molecular formula here is going to be CH4. That's actually going to be a condensed formula as well. So that's fine for methane. And in this case here, we're actually going to write the word name, the IUPAC name. They're going to assign meth for the prefix. The prefix meth means there's actually 1 carbon involved. In fact, everything with that prefix, methanol, methanol, meth anything actually means there's 1 carbon. The A and E actually tells you you're in the alkane family. This right here reminds you that we're all single bonds. So no double bonds in sight. In this case here, it's the simplest organic compound because you just have the single carbon. Let's go one step harder here. The next biggest alkane, let's do 2 carbons. So being 2 carbons, I at least need one of my arms to actually hold the other 2 carbons. Because every carbon has the equivalent of 4 bonds, I can know right away, this would be helpful in chapter 4, I know right away that there's going to be every hydrogen, there's going to be 3 hydrogens on other carbons there. So in that case there, I can condense it, I can count it up, I can say, well, for every 2 carbons, I actually have 6 hydrogens. This guy here is called ethane. We already saw this when we talked about sigma bonding and pi bonding earlier. Eth is the prefix for actually 2 carbons. Now the prefixes that used to be like 1 and 2, mono and di, will show up somewhere else, but at least in terms of the parent name here, meth stands for 1, eth stands for 2, and we're still in the A and E family. We're still in the alkane family, the single bonded family. In some sense, I want to start showing you, as this molecule here gets larger and larger, the structural formula is going to take up way too much room. The structural formula here is all the detail. It shows all the bonding. It almost shows the Lewis picture for everything. Well, all it doesn't show is the Vesper geometry. Molecular formula is nice and simplistic, but of course, it may be a little bit too simplified. So we're going to get the best of both worlds with what's called a condensed formula. A condensed formula will condense little bits of it, the parts that really don't matter here. For example, the H's, I just assume they saturate this carbon here. I would actually write this here as CH3. That carbon is bonded to 3 other hydrogens. Then I'm going to draw the other carbon. I've condensed the hydrogens. I haven't shown you all the detail of how the hydrogens are attached, but I've noticed that condensed structure leaves the carbons sort of in order here, and therefore I can still see, oh, it's these 2 carbons that are connected together. Even though I write the H's in between here, I know the H's can't actually be in between molecules. They have to be terminal, so I know I would expect the carbons are bonded to each other. So in that case there, that's where we get the condensed formula, a little bit of a middle ground between the 2 of them. In fact, sometimes even condensed formula, they might even say H3C and then CH3 like this. All they're trying to do is they're trying to say, well, these H's are actually on the left-hand side of the carbon. So these H's here are attached to this side of carbon. Whether you write it this way or this way here, it's exactly the same thing. So that one, there's the condensed formula. Let's go one step bigger here. We're going to get 3 carbons. So 1, 2, 3. We're all single bonded. We're all still in the alkene family, just hydrocarbons here. Let's imagine carbon can make the equivalent of 4 bonds. I want to start showing you a pattern here that, with the exception of the 2 carbons on the ends, this carbon here can actually hold 3 hydrogens. Anytime I have hydrogens that are in the middle, they don't have to be smack in the middle, but if they're not at the end, if they're not terminal, they're actually using 2 of their arms to hold carbon. That only leaves 2 extra arms to hold hydrogens in the middle. So if I did a condensed formula here, I would say ch-ch-ch. So I've condensed the hydrogens, and I would imply that the carbons themselves are connected to each other here. And therefore, I'm going to write down here, this is going to be C3, H8, right? Just counting up how many C's, how many H's. This guy here we use in a lot of our barbecue stoves here. This is just propane gas. In fact, these very light molecules here, we see that they're nonpolar because they're just C's and H's. Their melting points are just going to break London forces, relatively weak. These really light alkanes here are really, really easy to melt. We're starting to get a pattern here. We're going to see every time I add one carbon, the hydrogens add by 2. So if I just follow that pattern here, one extra carbon means I have 2 extra hydrogens. Great. So that is a nice pattern. The only thing I don't like about this pattern here is this one here relies on the one before it. It would be nice if I had a formula that just links directly the carbon number to the hydrogen in that same molecule. So we're going to derive that in just a second here. Let's do that right now. So what I'm talking about here is we're actually going to come up with a general formula, a general pattern that alkanes follow. What we're going to do is we're actually going to, I remember I had an epiphany moment one time when I realized this here. We're going to look at a molecule like propane, and we're going to say, at the very least, every carbon has 2 hydrogens. This carbon has 2 hydrogens, this carbon has 2 hydrogens. So at the very least, my general formula should be, for any number n of carbon, the hydrogen should be 2n, because every carbon holds twice as many hydrogens. There's only 2 exceptions here, is the hydrogens on the ends, because this carbon here that's terminal is no longer holding yet another carbon along the chain. This is holding 1 extra hydrogen, another extra hydrogen. We need to add a +2 at the end. This is the general formula. This is that pattern that associates how many carbons to how many hydrogens you have in that compound without relating to the one earlier. So if I fast forwarded and if I said, what about the alkane with C100? I don't have to write 99 other alkanes and just subtract the +2. I would say, well, easy. All 100 carbons, everyone at minimum will have 2 hydrogens. 2 times 100 is going to be 200. 200 plus the 2 there would give me a total of 202. If you had the time to draw it out there, you'd find that that is exactly the structure that we need. We say, again, the name, we're seeing it coming from the carbon bits of it. We'll do more with the naming of it here. That's the general formula for an alkane. We refer to alkanes as saturated. Saturated, we've used in our solubility section. Saturation means you pack it full. It can't handle dissolving anymore. In this case here, we're saturated because the compound is containing the max number of hydrogens. We actually have the maximum number of attachments. When we later on form multiple bonds like double bonds and triple bonds or form rings, we end up losing hydrogen. We end up getting unsaturation. That's actually where they get the terminology of saturated fats and unsaturated fats. Let's move on here to the next biggest alkane, and then we'll do more with the naming. The next biggest alkane will be C4H10. Structural formula, we're going to draw just 4 carbons in a row. We just said every carbon has the equivalent at the least saturated with the rest hydrogens, and we're expecting that the 2 carbons on the end have 1 additional hydrogen. You can check the 2n plus 2. That's exactly what we want here. This guy here, the prefix for 4, you can condense it as well. The prefix for 4 is going to be butane. So we had meth for 1, eth for 2, prop for 3. But actually means 4 carbons. Butanol, butanal, butanone. But just means 4 carbons involved. In fact, in this case here, we can actually sometimes refer to this as N-butane. As the chain itself is starting to get longer and longer, sometimes it might not actually be just one long row of them. Sometimes we're going to see in the next example here, it actually branches off. So the N just actually relates to this being a straight chain. They're just confirming for you, no, these 4 carbons are all along a row, and we get this straight chain alkene. What else can I do to this? This is actually referred to as structural isomerism. With the formula C4H10, I can actually draw a different structure. And how this works here is I'm always going to start off with the longest chain. Imagine they're all in one long row. That's the only variation I could have. Then what I'm going to do is I'm going to imagine breaking a bond. I'm going to imagine taking this CH3 grouping. We're going to call it a methyl group in a second here. And what I'm going to do is I'm going to think about trying to reattach it somewhere. So the methyl group itself is a CH3. I can try reattaching it. Let's just practice here. If I try taking this one here and I try to reattach it on this H here, this one here would actually be exactly the same molecule. Even though it looks a little kinked on itself here, we still have 4 carbons in a chain. It's still going to be exactly the same molecule. It's just slightly conformed, slightly twisted on itself. So that doesn't work. I can try to reattach the CH3 grouping here on the 3rd carbon. So I cut it off, the 3rd carbon, and I can put it on. I can put it back on here. Same problem here. That would be the same molecule because that one there is also 4 carbons. So for this molecule here, because the long chain here, it's fairly short, it's only 4. I can actually reattach the CH3. What if instead of reattaching to the ends, what if I reattach to the middle? What if I replace this hydrogen with the methyl group, I move the hydrogen back there? This wouldn't naturally happen. It wouldn't interconvert like this. But what I can do here is imagine subbing on that CH3 group over here. Let's make sure we're still the same compound. Every carbon has the equivalent of 4 bonds. So I have 1, 2, 3, 4, 5, 6, 7, and I have 3 extra hydrogens. I'm still C4H10. This one here only has 3 carbons in the chain though. At maximum, I can't actually string together all 4 carbons. So in this case here, the relationship between these two, again, we're going to do a whole chapter on this next year. The relationship we're going to call these ones here, these are structural isomers. They're structural formula. They're all the details of how things are bonded. They're the same in some ways. In this case here, to be structural isomers, we have the same molecular formula. We have exactly the same C4 and H10. But in this case here, what's different about them is they have a different structure or they have a different bonding. So in this case here, we see first one was 4 carbons in a row. This one here only has 3 carbons in a row. So as we start switching over to a little bit of naming of this one here, we need to be able to come up with a clever enough name that regardless, like earlier, maybe it may be twisted on itself. Sometimes it's the same molecule, sometimes it's different. I want to come up with a clever naming scheme that will actually be able to differentiate you're this molecule or you're this molecule. So these are structural isomers. As you can imagine, if I start getting more carbons and more hydrogens, there's more opportunities, there's more ways I can actually branch off. We're going to call this sort of longest chain the parent. These are going to be called branches that branch off that parent there. So those are called structural isomers. They are different in structure or different in bonding. And we refer to these ones here as alkyl branches because they actually are carbon branches. So let's just learn sort of You Pac system of naming. Actually a fairly simple way of naming. First thing you could do is I want you to find the longest carbon chain. Take whatever molecule that you're looking at. Let's say I'm looking at this one here. Start from any side of the molecule to any side of the molecule, any ends of the molecule, and find the longest uninterrupted carbon chain. So in this case here, I'm going to circle. If I start on this side, I could go 1, 2, 3. You may have decided to go 1, 2, 3 like this, right? Doesn't really matter, right? This thing here would be twisting, single bonds. They're sigma. They're connected along the internuclear axis. They can twist no problem. So find the longest carbon chain. This part of the name is going to become the parent. The parent chain, the parent skeleton here, this is going to be your prefix methyl, ethyl, propyl, butyl, things like that. In this case here, my longest chain, no matter how I draw it, is going to be 3 carbons. I use my prefixes methyl, ethyl, propyl. In this case here, my parent has 3 carbons, so we're going to name this one here propane. Prop, because I have 3 carbons. I'm going to show you these prefixes in a second here. So I have 3 carbons, but we are still in the alkane family, so we are still single bonded. I try to give you sort of the maximum information in the sort of the least amount of space. So that's just propane. If you compare this molecule to the one that we had earlier, propane also had 3 carbons, no problem, but propane was saturated the remaining with just regular old hydrogens. If you look at this molecule, doesn't matter which parent you do, you can do the 1, 2, 3 going across. I'm just happen to do this one kind of going up on the side. Propane does have 3 carbons. It does basically have H's on everything else. The only part that I have not named is I've actually removed what would have been a hydrogen ending. I pulled off that hydrogen and I actually subbed on a carbon branch. We remember from butane, that carbon branch here was chopped off the ending of that 4 carbon chain. In this case here, the branch itself, I still have to name. It generally will have this formula here. The branch comes first and the parent comes afterwards. The branch will also use the prefixes here. The prefix for 1 is meth. And for a branch, we call this one here an alkyl branch, as I mentioned earlier, because the ending here, alkyl group, is a carbon branch. Because of that, I'm going to use the ending YL. So instead of calling it methane propane, I'm going to call it this will be second step. Second step here, I'm going to name the branches. So name the parts that are not part of the parent yet. Name the branches and number the parent. I'm just going to show you how that works here. So I have a parent that's carbon 1 to number 3. In this case here, I have a 1 carbon branch. The 1 carbon branch is going to be a meth. Meth means 1. But this is because it's a branch, it has a YL ending. This is going to be a methyl. but I do want to know where that methyl is actually branched off of. For my parent that's 3 carbons long, I can count sort of left upwards like this: carbon 1, carbon 2, carbon number 3, or I can count the other way: carbon 1, carbon 2, number 3. In this case here, the methyl is branched off position number 2. I'm actually going to put the number where this is branched off the parent. The number will be separated by a hyphen. This guy here is actually called 2-methylpropane. We're going to see structural isomers are actually going to be have different You Pac names, and that's actually a nice indication it's not just a twisted form of it. It actually is a slightly different molecule. Different London forces, as you saw in yesterday's lesson, but that's how the naming is going to go. This is the position. This is where along the parent it is. Numbers and letters are always separated by hyphen. That's important for You Pac. The meth means I have a 1 carbon. The ending of it, the YL, tells you that it's a branch. So we would have been a propane, except that on position number 2, we actually happen to have a 1 carbon branch. So let me just go over some of these prefaces, and then we can practice some more here. Let's just count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I just showed you the parent 1 to 4 is a little bit weird. We had meth, eth, prop, but. So that's 1 to 4. We used to say mono, di, tri, tetra. Again, that part will come back a little bit later. Fortunately for us, from 5 on to 10, it's all the same. So hopefully you're able to say here, this is going to be penta, 6 is going to be hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. There is 11 and 12 as well. You can Wikipedia for those endings, but typically we just end off at 10. So we have those prefaces there. If it's the parent, we just add the suffix like methane, ethane, octane, heptane. If it's a branch, we're going to end off the ending with YL. Hexyl, octyl, propyl, ethyl. That's actually how you're going to name the branch. So let's just do a few examples of this one here. Let's take a nice long chain here. Let's go 1, 2, 3, 4, 5, 6, 7. Let's go 1, 1, 2, and 1. Okay, so a lot harder than the one we did before. What I'm thinking here is, although I've only drawn for you the hydrogen bits, I know every carbon always has the equivalent of 4 bonds, 4 attachments. So you can assume that there's actually going to be CH3. This one I already show you 3 H's, or 3 bonds, so that's only one other H, CH3. I'm assuming there's actually H's that are subbed on the rest of these chains here. But because that part there doesn't influence my name, I'm just going to focus on just the carbon shape. So let's do our You Pac naming rules. You Pac said you're going to find the longest chain. Start from any side to any side, and you're going to try to find how long that carbon is. Remember, you can go from any side to any side. I could start from, let's say, over here. I can go 1, 2, 3, 4, 5. I can start from this side, 1, 2, 3, 4, 5, 6. I can start from this side, 1, 2, 3, 4, 5, 6. I can start from this side, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. You're basically counting back and forth. You're trying to find the longest one, because that's who the parent's going to be. Hopefully you're able to find for me here, the longest chain is actually a 7 carbon parent. It actually does do this zigzagging, because if you think about being tetrahedral geometry, all of these are actually 109.5, so they do actually kink back and forth. My parent happens to have 7, so I'm going to use the prefix for 7, which is hept. So far I'm still in the alkane family, so it's going to be heptane, A-N-E. The part that I have not circled, I still have to name. So what would we call this branch here? This branch would have been a hydrogen, but now it's a 1 carbon branch. Like earlier, the prefix for 1 is meth. The ending is YL. This is called a methyl branch. Similarly, this one here is called a methyl branch. These branches that are branched off the trunk of the parent are 1 carbon apiece. There's a slightly longer branch here. This next branch here actually has 2 carbons in it, and in that case there, we're actually going to refer to it as an ethyl branch. Careful the difference between the branch itself has 1 carbon, although I have 2 of them, versus in this case here, this branch by itself has 2 carbons already. This is now 1 single ethyl branch. In this case here, there's 2 other rules. First rule here is we always alphabetize the branches. If I have many different endings, if I have one starting with ethyl and one starting with methyl, the E for ethyl comes first. I do need to number the parent, so I know I have 7 carbons in a row, and there is a rule for numbering. I want to, in general, keep the numbers small. I want the branches to occur at the lowest possible position for simplicity. So here's what I'm going to practice here. If I try to number it top down, I would number, remember I'm numbering the parent, carbon number 1, 2, 3, 4, 5, 6, 7. If I write for you where those branches are, I see the methyl branch off at 2. Ethyl is branched off position 4. Another methyl at branch number 5. You don't need to do this, but I'm just going to show you 2, 4, and 5. What if I numbered it the other way? This turns out to be the wrong way this time. 1, 2, 3, 4, 5, 6, 7. That time, the first branch, actually, I have nothing at 2. My first branch actually occurs at 3, 4, and 6. I don't really need to look at sort of all the branches. I'm looking for the first position that's different. I want to keep the branch at the lowest number possible because the 2 way is going to be lower. I'm not even going to bother with this blue way of numbering it here. I've numbered the parent so my branch occurred at the lower 6 position. Sorry, lower 2 position. So in that case there, I've already decided which way of counting it, and now it's just a matter of numbering and filling it in. E comes first, so the ethyl is branched off position number 4, so this would be a 4 ethyl. We're going to then need to name the 2 methyl branches that we have. We have one methyl on position 2, the other methyl also position 5. Instead of saying 2 methyl and 5 methyl, that's a little bit cumbersome. What we're going to do is we're going to just sum that up, and we're going to say 2, 5. At position 2, at position 5, we're actually going to have a dimethyl. That's where that mono and the di show up again. This di part represents 2, and there's 1 carbon branch. One of them's on 2, and one of them's on 5. Now, although I have just made this emphasis, oh yeah, keep the numbers small and alphabetize and all that, you'll notice sometimes because of the alphabetizing, E actually comes before the M for methyl. I don't worry about the mono and di when I'm alphabetizing. Because the ethyl actually happened to be a little bit longer down the chain, this number is out of order. That's perfectly fine because the number, that set of 2, 4, and 5 were already the tinier numbers than 3, 4, and 6. It's just because of the alphabetizing I may be out of order in that You Pac name. So just be careful of that. As we look at a few other examples, might help you with that. So far, that's sort of the main way of doing the naming. You do need to memorize these prefixes here. So far, these have all been hydrocarbons because they have just been C's and H's. We can start substituting, instead of hydrocarbons, C's and H's, we can actually sub on our halogens. Halogens can also, like that methyl or ethyl ending here, we can actually sub on instead maybe a fluorine branch or maybe a bromine branch. It's just the ending here we're going to call fluoro, bromo, chloro, and iodo. So this right here is just a summary of what we did. We talked about it being saturated. Single bonds here are sigma bonds. Sigma bonds are along the internuclear axis, so there is no pi bonding involved. Single bonds here allow for free rotation, whereas as we switch over to cyclic compounds and multiple bonds, these ones will start getting double bonds and pi bonding. If I really did have a pi bond, if I really, on top of the sigma bond, if I had a pi bond which is a sideways overlap, this one here wouldn't let for any twisting, because if I twisted one of them, I'd physically be breaking the bond there. Not impossible, but it naturally doesn't want to do that. So let's just practice here. I'm going to take a look at a cyclo compound. We're going to add the prefix here cyclo beforehand, and I'm going to throw on some of these halogens as well. So let's just do this over here. Let's take a ring. So far we had butane. So butane was like this. This time, instead of butane like that, let's form 4 carbons in a ring like this. Are these structural isomers of each other? Are these the same formula, or are they different? So let's check the formula here. We can do the 2n plus 2 if you like. N is equal to 4, so 2 times 4 is 8. That means I have C4H10. In this case here, I also have C4. Every carbon has the equivalent of 4 bonds, but you notice there are no terminal carbons anymore. Every carbon is holding 2 other carbon neighbors. If every carbon has the equivalent of 4 bonds here, I notice I can only hold a maximum of 8 hydrogens. In that case there, I notice that these two have different formulas. These two, make a note for yourself, these are not structural isomers. The ring form and the non-ring form, these are not structural isomers. They have a different formula. And that's actually because, shouldn't really surprise you here, if I was a long chain like this, or even if I was branched off, if I was put on that second carbon again, I actually do have 2 extra arms to hold hydrogen. I need to ditch the 2 hydrogens on that end, get my unpaired electron back, and I need to sort of ring around here, and I need to bond to the other neighbor. I would have lost those 2 hydrogens. We have gained a degree of saturation, lost 2 hydrogens, and we become, so let's say 1 degree of unsaturation. So saturation, remember, I meant fully packed, fully, that's the maximum number of hydrogens I filled. In this case here, because I'm arbitrarily ditching the 2 hydrogens and bonding those 2 other chains together, I'm definitely unsaturated. This guy here, we can still call it a butane, fortunately, because our parent is going to be still 4 carbons. Just to remind you it's a ring, though, I'm going to call this one here cyclobutane. It's a ring of 4 carbons together. So that becomes a prefix. We're still a 4 carbon, and we're still a single bond this way. In terms of numbering and naming and whatever, let's sub on a fluorine group. Let's sub on a bromine group, maybe like that. So I'm going to call the fluorine a fluoro, a Br a bromo group. When I number, this is like the age-old question, where does the circle start? I want to start the circle where there is a branch, because that would keep the numbers tiny. So in this case here, let's start carbon number 1. Up to you. In this case here, I know brome is going to be alphabetized first. So let's start carbon number 1 here. I could have counted clockwise or counterclockwise. I'd rather count counterclockwise this time, so my numbers are going to be 1, 2. I'm trying to keep all the numbers tiny. So let's alphabetize here. This one here, this later compound would be called 1 bromo, 2 fluoro, cyclobutane. Numbers and letters are always separated by hyphens, and then letters and letters, you can just sort of ram them into each other. So that's how you deal with, it's not a hydrocarbon anymore, it's not just C's and H's, but I just subbed on some halogen groups there. As we get to some alkenes and alkynes, we'll do another practice here. We did a lot of the basic naming using the really simple family of alkanes, and now what I want to do with you is I want to go through 2 other families. Let's start making the parent different. And how they're going to be different is they're going to introduce, these are later on going to be called functionalities. They're special groupings that the molecule might have that gives the molecule a very particular behavior. So an alkene, very similar naming to an alkane from earlier, an alkene will at least have 1 double bond. They actually want to specify that that double bond has to be between 2 carbons. Up to this point, everything has been single bonded, everything has been saturated. Double bonds at least will make it an alkene. If I have at least 1 triple bond here, again, the emphasis there is it has to be a triple bond between carbons. We actually are in the alkyne family. So instead of earlier methane, ethane, propane, we're going to then change the ending to ene or yne instead. There's just one little caveat here. You're still going to find the longest carbon chain. In this case here, I don't know if I wrote it, the chain, the parent must include the multiple bond. That multiple bond is so special to the molecule that the parent has to run through the multiple bond. That multiple bond takes the priority, so that number of that where the multiple bond is always going to be the smallest number possible. So let me just demonstrate what I mean here. So let's take the molecule, scroll down here. Okay, so let's go. New example, this one here will be an alkene example. Alkene I'm expecting is C double bond C. So let's go 1, 2, 3. Let's do this. All right. So based on what I told you earlier, based on what I told you earlier, you would say, okay, find the longest carbon chain. I even add on a chlorine just to try to confuse you here. Chlorine, although the symbol does also start off with C, that's not carbon, so don't start there. So finding the longest carbon chain involves finding, let's actually do 2 chlorines here, sorry. Finding from one side of the molecule to the other side of the molecule, how many carbons can I string together? Without worrying about this alkene, you could have started at the carbon. So there's a C. I can count 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. If I count from this side, 1, 2, 3, 4, 5. You can start from any end of carbon to the other end of carbon. You want to find the longest chain of carbon. Based on the alkane stuff that I told you so far, you would have said these 6 carbons here is my longest chain. The only problem with that here is it doesn't actually go through that double bond. That double bond here actually takes priority. That double bond is actually really special to this molecule. So the limitation here is even though I could have gotten a longer chain this way, I'm actually going to, sorry, let me drop off that C there. I'm actually going to draw the longest parent I can, but draw it on. Let me drop the C out. I am actually going to draw it going through the double bond. So if I have to go through this one, you can either turn to the left and make it 4 carbons long. You can turn to the right and make it 5 carbons long. Well, 5 is longer than 4, so there we go. We're going to have that 5 carbons there. Okay. Sorry, now that I've edited this molecule, you can name it properly. Okay, so we talked about here, although technically it would have been 6 carbons long, because the longest chain has to go through that parent, I'm stuck with doing 5. The prefix for 5 is going to be pent. The ending is going to be ene, like the shampoo, so pentene. And in this case here, because this double bond here could have been anywhere along that chain there, my double bond here takes priority. The double bond here is very special. When it takes priority, I'm saying this one here always takes the smallest number. So my double bond currently here goes from carbon number 1 to, it stretches from 1 over to 2. You can call this one here a 1-pentene. Up to this point, we've been using numbers for branches. In this case here, I'm talking about the ene, the double bond. The double bond starts from this position here, position number 1. And I imply there it stretches from carbon number 1 to carbon number 2. Now, why did I try to edit all this here? In fact, if I was doing a regular naming, I should have actually counted from this side, because I would have a fluoro at 1, I would also have another fluoro at 1, but note, the double bond itself actually takes priority, so therefore, I'd rather fine. I have both of these at 5, so be it. I also have, in this case here, a 2-carbon branch. We saw that from before. That's an ethyl branch. It's branched out position 2. E for ethyl comes before F for fluoro, even though it is going to be a difluoro later on. So the full name of this, if you practice out here, this should be a 2-ethyl, and then we're going to get a 5,5-difluoro. Right? 1-pentene. So this is the You Pac way of naming it. No matter how this molecule later on twists on itself here, I know this should be the name. Sometimes for this number here, especially for the double bond, sometimes they write it inside the name. So they might call this latter part here pent-1-ene, exactly the same thing. They're just trying to tell you the double bond, which is so special to the molecule, actually starts on position number 1. Let's try out a compound with alkyne. And alkyne here has a CC triple bond. Let's even do it in a ring, just to make it confusing. So let's do 8 carbons in a ring. Although realistically, I can have a molecule that actually has multiple rings together. We're going to simplify things. We're only always going to have just either 1 double bond or 1 triple bond or 1 ring. It's not going to actually be 2 rings. And that ring by itself is going to be the parent. So even if I have longer carbons that are branched off here, I cannot count it, carbon number 1, and then count into the ring. The ring itself would be the parent. So let's just sub on a few groups here. Sure, let's sub on that Cl. 1, 2, 3. Let's sub on a I group. Let's sub on another I. Sometimes I use a condenser here. Let's do C3H7. And what that condenses here is, it actually condenses that there's actually 3 carbons involved. It's actually 1, 2, 3 like that. If you count up how many hydrogens would have been attached, that's 7. How did I know that so quickly? 2n plus 2 would have been 8. I would have to ditch 1 bond so that I can attach to this carbon here. So I know it's going to be C3H7. So the ring is going to be my parent. My ring happens to have 8 carbons. So this is going to be a cyclooctane. When I number it, the multiple bond takes priority. So this triple bond is a very special group. It's either going to be carbon number 1 and carbon number 2, and then clockwise from there, or it's going to be the other way, carbon number 1, carbon number 2. So in that case, the triple bond doesn't really show me which other branches will be lower. Let's keep counting around here. When I go 1, 2, my first branch is at 3. Counting the other way, I have 1, 2, 3. My first branch is at 4. I'd rather count it the green way. So in this case here, let's just count it around the ring here. 5, 6, 7, 8. And in that case there, let's name the rest. Let's alphabetize it. This one here is called a propyl branch. This is called an iodo branch. This is called a chloro branch. Chloro alphabetically comes first. So this is going to be 3 chloro. Next one is going to be a 7 iodo. And then we're going to have a 6 propyl. Cyclo. Oh, sorry, it's not even a cyclooctane anymore. We have cyclo. Sometimes they put that 1 there to show you that the triple one actually starts from position number 1. The oct was right because we're 8 carbons, and we're actually in the octyne family, Y and E, because alkynes have a triple bond. As we get into this organic a little bit more next year, we're going to find alkenes actually have another type of isomer. Unlike structural isomers, which differ in bonding, we can have what are called geometric isomers. They involve sort of those branches being on the same side or their opposite sides. Because the double bond itself doesn't rotate, that sigma and pi bonding here doesn't naturally twist. If we're on the same side, we're going to call it the cis isomer. If we're on the opposite side, sort of going across the double bond, we'll call it the trans isomer. Next year, we're going to summarize that in sort of EZ isomerism as well. More on that later on. Usually Z is going to be cis, and they use a really corny acronym. They say Z or cis is on the same side. Just try to do for yourself here. Cis is somehow we're along the same side of the double bond. Right? So here's the last little bit here. we started looking at these special groupings that actually give the molecule particular behaviors. We call these groups in general functional groups. They're groups that give the molecule a certain functionality. They give it a very special property. I made a listing of these groups here. Eventually, yes, you'll need to know the names of these ones here and the names of those functional groups, and then also the name of the ending. Some groups that you've seen already here is earlier we had done cho. Actually, this cho grouping here, when you draw it enough times, you actually realize this cho is always C double bond single bond H. So as it pertains to chapter number 4, if you see a cho, that's actually going to be this functionality. When you look like that, the ending is actually going to be Al like that, but at least it helps you draw the picture. We know it's polar, we know it's going to be dipole-dipole, all that earlier. So that's an aldehyde. A ketone very similarly, so it's a different name of the family. It's shorthanded CO like that, so maybe I have CCC and I have a double bond like this. That would be this CO grouping. So if you sort of know how these ones are sort of summarized on each other, you can actually draw the molecule quite quickly. Benzene itself, benzene we had seen is going to be C6H6. Benzene already is a ring, so we don't have to say cyclobenzene, and benzene can be substituted. I can replace the hydrogen. We'll see some reactions of it next year that could actually swap out this hydrogen here. We saw this Cu molecule from before, Cu. If you remember when we actually drew it, when that COH gets drawn out, it's always C double bond O single bond OH like that. So again, if you recognize the functionality, it can actually save you time in actually trying to draw these molecules. Let me end off with one of them here, and that's going to be a combination between that Cu group and an amine group. We're going to call that there an amino acid, building blocks for a lot of proteins. An amino acid is actually a combination of an amine, and the acid part is a carboxyl group. It actually has an amine, which is an NH2 on one side. So NH2 ends usually have a lone pair. We have a carbon in the middle. We have that Cu group on the other side, so C double bond O single bond OH. For an amino acid, one of them is an H, and the other group here we typically just call it an R group. The R group just stands for the remainder of the molecule. That could be as simple as just another hydrogen, or maybe a long hydrogen chain, carbon chain, maybe a benzene ring or whatnot. But basically, our building blocks are proteins. We have about 20 amino acids. They're all left-handed. We'll talk about what that means next year. But they do have these two functionalities. They have the amine functionality and they have the carboxyl functionality. And we're going to see next year a reaction where if I have an amino acid as a building block, if I put another amino acid right beside it, these building blocks here can react together and they can actually join together, forming what's called a peptide link. So again, this is just a quick crash course on organic chemistry here. I did want to introduce to you that You Pac naming. No, you're not going to be tested on name this compound in this chapter, but again, it's just to make sure you're on par with your regular grade 11 peers, and also maybe in recognizing some of these functionalities, maybe it'll help you with drawing your Lewis pictures. All right. So if you have any questions, just let me know. Thanks, guys.